We're back outside again, and I wanted to talk about something called the Hall effect. So the magnetic field also affects how charges move inside a conductor, and one result of that is called the Hall effect. So right here I have a conductor. The conductor is between these green lines here, and my conductor is inside a magnetic field. And the magnetic field here is pointing into the ground. That's what the X means. The magnetic field is pointing into the ground right here. And the current running through this conductor is pointing off in this direction. So if we know that the current in my conductor is moving in this direction, then my electron, which I'm denoting right here with this red dot, must have a drift velocity in the opposite direction of the current. And so my electron is actually going to be heading off in the opposite direction that we define the conventional current. So if I use my right hand rule here, I put my fingers in the direction of the magnetic field into the board, and I put my thumb along the direction of the magnetic field. Now, the thing about the right hand rule is that the direction that my palm is facing, that would be the direction of the magnetic force for a positive charge. But for a negative charge, the direction of that magnetic force is actually on the back side of my hand, or on this way, on the top side of my hand, on the opposite side. So the direction of the magnetic force is not going to be pointing in this direction, like it would be out of my palm. For a positive charge, it's going to be actually pointing out of the top of my hand in this direction for the negative charge. So this particle is feeling a negative charge, a negative magnetic force that wants to point it upward, move it up to this top edge here of this conductor. And so all of those electrons then, when they're feeling this, they're in the current and they're experiencing this magnetic field pointing into the ground, they have a magnetic force that's going to be immediately pointing upward here. And so all those electrons are going to want to come up and pile up onto the top side here of this conductor. And they're going to build up a negative charge on this side of the conductor. Okay, and so that means there's going to be a charge separation. So the other side of my conductor is going to have a positive charge. And so what happens when you have a separation of charge in a conductor, we saw something like this when we were talking about capacitors, and whenever that happens, we set up an EMF, a potential difference, across these plates here, okay? And so now we've built up an EMF, and this is what we call the Hall EMF, okay? And it's because we are able to create this separation of charge when we have this conductor with a current running through it inside a magnetic field, okay? So although this magnetic force moves negative charges to one side, we cannot build up the charges on these conductors on the edges without limit. And so the electric field caused by this charge separation opposes the magnetic force, and the electric force acting on this electron here eventually grows to equal it. So eventually we will reach a state where the electric force, which we can write as the charge times the electric field, equals the magnetic force acting on those particles, which is equal to the charge times the velocity of those particles, the electron, times its magnetic field, okay? So the charges cancel out from each other, and then you're left with just this expression that the electric field is equal to the speed of those electrons, this would be the drift speed of the electron, times the magnetic field here, okay? And if we remember back from one of our earlier chapters when we were talking about electric field, that whenever we have two parallel plate capacitors, for example, the electric field between those two parallel plates is equal to that potential difference across those plates divided by the distance between those plates. And we can also write that as being equal to, for instance, in this setup that we have here, being equal to our EMF that we've induced divided by what I'm calling L here, which is the width here of my conductor that I've drawn here. Okay, and so we can rewrite this and say that since these are both equal to E, that the velocity of the drift velocity of the electrons times the magnetic field is equal to our induced Hall EMF divided by the width of my conductor. Okay, so VB is equal to our epsilon, which I'm representing as the Hall EMF, divided by the width of this conductor here. And so we can solve that for the induced Hall EMF, and the EMF is equal to the speed, or the drift speed of those electrons, times the magnetic field times the width of my conductor here. And so finally we arrive at our equation for the Hall EMF. And this is a special case where the plane of my conductor and the direction of the velocity of my charge and the magnetic field vector are all perpendicular to each other. So this is a special case. And so our Hall effect here again is the voltage, or the induced voltage, that we can set up across a conductor of width L through which moves some charge with speed v. Now the Hall effect was really useful for us, and it actually was the thing that was used to determine that electrons are the charge that carries current, not positive charges. And there are devices called Hall probes, which are used to measure flow based on the EMF that this flow can produce. And some examples of Hall probes can be used to measure blood flow through blood vessels, but they can also be used to measure fluid flows in large laboratory experiments. So we're going to use the Hall EMF in order to solve a problem right here, where we're going to use the Hall EMF to think about how fast blood can flow inside our artery. A Hall effect probe is placed on an artery to measure the average blood flow velocity. The probe records a Hall EMF of 80 microvolts when a magnetic field of 0.08 Tesla is applied. So given the artery's diameter of 3.8 millimeters, what is the speed of the blood flow? Right, so here, we can imagine this is our artery, and it's got some width, L here, of 3.8 millimeters. And we're applying a magnetic field across that artery of 0.08 Tesla. And we're able to measure a Hall EMF, a potential, across the artery. So we can find the speed of the blood flow, the speed of those charge carriers, which is essentially the blood, through the artery here, by using our equation for the Hall EMF. The Hall EMF is equal to the applied magnetic field times the diameter of our artery times the speed at which the blood is flowing through the artery, and that blood is our charge carrier in this case. So if we solve this equation for V, the speed of our blood through the artery, V is equal to the Hall EMF divided by the magnetic field times the width of the artery. So our EMF here was given to be 80 microvolts. So that's 80 times 10 to the minus 6 volts. And we divide it by the magnetic field, 0.08 Tesla, times the diameter here of our artery, 3.8 millimeters. So that's 3.8 times 10 to the minus 3 meters. We take that operation in our calculator, and we find that the speed of the blood flow inside our artery, by applying the magnetic field, measuring the potential difference across the artery itself, we find that the speed of the blood then is 0.263 meters per second, or 26.3 centimeters per second. And yes, a similar thing is done in order to try to measure blood flow in different arteries or veins in our body, so doctors can better diagnose conditions.